Previously, we inserted new node into an AVL tree. Now let's talk about AVL deletions. So we want to delete a node from AVL tree. So simply deleting is not that hard. Okay, so we have to find out where it is, where the target node is. Okay, then we just delete. We did that with the BST, right? But if it is AVL tree, then we have to make the constraint. We have to preserve that constraint. So when we delete a node, then we might break the conditions, the constraint, okay? So that's what this slide says. Basically, delete a node by deletion algorithm of binary search tree. Okay, so far so good. That's not that hard. And then second step says if the tree becomes unbalanced, then we have to rebalance it. And when we delete a node, then there are 6 possible cases when the tree is not balanced. Okay, so we have 6 cases, and these 3 are symmetric to these 3. So we are gonna focus on these 3 cases. Okay, and then the other 3 cases are exactly the same as this. First one, R0 case. So before deletions, our subtree looks like this, okay? And we have A, B, and we have subtrees here. And this number is the BF of A and BF of B. So R0 means when we delete one node, and when we delete one node from here, then the height of this subtree is H minus 1, and the BF of B is 0. So we didn't touch in this subtree, so the BF of B is 0, and still it is 0, okay? So after deleting one node from this subtree, then the height of this subtree becomes H minus 1, decreased from H, and BF of B is 0. This 0 is coming from this. Okay, then what should we do? We should rotate the subtree to balance. Okay, so in this case, actually B goes up and B is here, and A goes down. So A becomes a right subtree of B. Okay, so A is here. So B left subtree is still here, so we don't touch this part. Okay, and then we don't touch this part. And this one, the right subtree of B will be the left subtree of A. Then let's check the BF. Okay, so the height of BL is H and the height of BR is H. Then the height of this one is H. The height of this one is H plus 1. We have H and we have one node, so we have H plus 1. So BF of B is minus 1. H minus H plus 1. Okay, and then BF of A is 1 because this one is H and this one is H minus 1. Good. So again, when we rebalance, okay, when we rotate this tree, then still we don't change the order. Okay, still BR, this one is left subtree of A. It means this one is smaller than A, but still BR is larger than B. Okay, so basically we didn't change the order from this. Okay, so BL is left subtree of B, so it's still there, and we didn't touch about this, and we actually changed and this one and the relationship between this one. But in this case, B is left child, so it means B is smaller than A, and in this relationship B is still smaller than A, and the BR is smaller than A and larger than B, and in this figure BR is larger than B and smaller than A. So we didn't change the order. We just changed the structure. Okay. And the second case is R1. Okay. So we delete one node from here. So from H, it becomes H minus 1. And R1 is coming from here. BF of B was 1 because the height of BL is H and the height of BR is H minus 1. In this case, we have to rotate because we have 2 here, so we have to rotate. So B goes up and A will be the right child of B, and BL will be here. We don't change this part, and we don't change this part, and this one will be the left subtree of A. So what is the difference between the previous slide and this slide? Actually, we didn't change. Okay, look at this one. It is a little messy, sorry, but basically the structure, this structure is exactly the same as this one. The only difference is BF. Okay, otherwise it's the same. The height is different and BF numbers are different. So BF of B is 1. It means the height of BL is H and the height of BR is H minus 1. So after rotating, the height of this one is H and the height of this one is H, right? So BF of B is 0 and BF of A is 0 because this one is H minus 1, this one is H minus 1. So we actually rotated in the same way, but we have different BF numbers. That's it. So basically R0 and R1 rotations are similar to each other. Okay, next one is R minus 1 rotations. Okay, and this minus 1 is coming from here. Okay, and we delete one node from here. So now this one is H minus 1. Again, sometimes when we delete one node from this subtree, sometimes the height doesn't change, right? In that case, there's no problem. Okay, there is no problem. I mean, we don't have to rotate anything. It's good as it is. Okay, but sometimes when we delete one node from a subtree, we decrease the height sometimes. Okay, so this is the case. And BF of B was minus 1 here. Minus 1 means this subtree, the height of this subtree is H, and this one is H minus 1. So H means we have one node here, so we have a couple of different, actually we have 3 different cases. And the maximum height of this one or this one could be H minus 1. Okay, so the height of CL can be H minus 1 and height of CR can be H minus 1. Okay, so depending on this B, we can have different BFs after rotation, but let's talk about the rotation first. So from B, after deleting one node from here, then this one is H minus 1 and this one is actually H plus 1 because we have H minus 1 and plus 1 plus 1. So we have H plus 1 here. So in this case, node C goes up. And this one is here. And this subtree is still here. And the CL will be the right subtree of B. And CR will be the left subtree of A. And C is here. So we had a similar case when we insert a new node, right? Okay, then after rotations, what is the BF of B and the BF of A? So it depends on the situations. We had a similar case when we inserted a new node, right? So depending on this B, we might have different values for B and A here. So let's check 3 cases. When B is 0, it means the height of CL is H minus 1 and height of CR is H minus 1. Okay. No, there is no other options here. So if b is 0, then the height of these two subtrees should be h minus 1. Okay, otherwise we cannot have 2 and minus 1 here. So if their heights are h minus 1, okay, then bf of b is 0, bf of a should be 0, because we have the same heights on the left and right subtrees. Okay, then next, if b is 1, okay, b is 1 means left subtree is longer than the right subtree. And then this one is h minus 1 and cr should be h minus 2. Okay, we cannot have h here. Okay, and the maximum of this one should be h minus 1. So if b is 1, then cl should have h minus 1 and cr should have h minus 2. There is no other option. Okay, then this is h minus 1 and this one is h minus 2. Then bf of b is 0, because we have the same height. Okay, and then bf of a is minus 1, because this one is h minus 2 and this one is h minus 1. So bf of a should be minus 1. And next, if b is minus 1 here, it means cr, the height of cr is h minus 1 and height of cl is h minus 2. There is no other kind of option here. Okay, then this one is h minus 2 and this one is h minus 1. Then after rotations, bf of a should be 0, because we have the same height. And bf of b is 1, because left subtree is longer than the right subtree. Okay, so this is the algorithm of the rotation after deleting. So let's implement. Actually, this is still an algorithm, okay, but it's close to the implementations. So let's delete one node. So we pass a pointer and we pass the key, and we have to find out where the key is. Okay, first we have to search, and then we have to delete that, and then if it breaks the constraint, then we have to rebalance. Okay, good. So if true is null, then we cannot do anything. And else if deleted key is smaller than root key, then we should go to the left subtree. So we call AVL tree, passing the left pointer and the same key and the same indicator. This shorter is actually corresponding to the unbalanced in the AVL insert functions. It's basically the same thing. Okay, and then after AVL delete functions, if shorter is true, then we have to call this right balance function. Okay, else if delete key is larger than root key, so this one and this ones are symmetric to each other, so we pass the right pointer with the same key and the same variable, and if it is shorter, then we should call left balance. So we have right balance and left balance, so it's symmetric. And else means node is found. Then we check a couple of different cases. First, there is no left subtree, so it's something like this. So this is our target node, okay, and we have the right child here, but we don't have left child. We have nothing on the left. Then delete this node, delete, and then attach is child pointer to its parent. So we have a parent here, so parent was pointing this node, and we are deleting this one, but this one has only one child, and the parent can point to this one. Okay, and that's it. And shorter should be true, because we delete one layer actually in this case. Okay, so from this one we take 2 steps, but after deleting we take 1 step to get here, and we didn't touch anything here, so we decrease the height of this subtree. So shorter should be true. and else there's no right subtree. This is basically symmetric to each other. Okay, so it's the same thing. So we have left subtree, but we don't have the right child. And then after deleting, this one should point this one directly. Okay, so symmetric. And the next one is more complicated. So we have two subtrees. So basically, parent is pointing this node, and this node has left subtree and it has right subtree. Okay, and then find the largest node in the left subtree. Okay, we want to delete this one and find the largest node from the left subtree. We did similar things right before, right? So find the largest one and copy this one to this node. So it is kind of deleting the original one, and we just copy this one. And then what should we do? Okay, we just copy it, and then we have to delete that largest one. Okay, so from this subtree, so the root left means this left subtree, and from this left subtree we have to search this largest one, and then we have to delete that. So we call this AVL delete function recursively. Okay, and then if it is shorter, basically this part is similar to this part. So if it is shorter, then we should call right balance. Okay, so I think this is kind of typo. See the next slide for this right balance. Okay, so now we have right balance function. So after deleting something on the left subtree, then if it is shorter, then we call right balance. Okay, so we deleted something on the left subtree, and we have a couple of different cases. First, if the root BF is 1, what does that mean? Okay, so we have root node. Root means in a big tree, so this root is the root node of this subtree that we are interested in. Okay, and this one is pointing the left subtree and right subtree, and we deleted one node from this left subtree. Okay, and then if the BF of this root was 1 before deleting, then after deleting one node from the left subtree, then the BF of this root node should be 0. Okay, it was something like this. It was h plus 1 and it was h. Then now after deleting it becomes h, so BF should be 0, and the shorter should be true because before deleting the height of this subtree was h plus 2, but now the height of this subtree is h plus 1, so it is shorter. Good. And else if the BF was 0, it means before deleting the node, then we had the same height on the left and right subtrees. So let's say this one is h and this one is h. Since we delete one node from the left subtree, okay, and then it is shorter, then this becomes h minus 1. So BF of the root node should be minus 1 because h minus 1 minus h is minus 1. Okay, good. But shorter is not true because we didn't change the height of this subtree. Originally it was h plus 1 and now it is still h plus 1. Okay, we didn't change the height of this subtree, so shorter is not true. And else means originally BF was minus 1. Okay, BF was minus 1 means originally it was h minus 1 and h. And now we delete one node from the left subtree and it becomes h minus 2 and h. Okay, then there is a problem, right? So we check the right subtrees BF. So there is one node here. if the right subtree BF is 1, its left subtree is longer than the right subtree, so it looks like this, then it is actually the right-left problem, right? Do you see that? Right, left is longer. That's the problem. That's why we have problem here. Okay, so if the right tree's BF is 1, it is RL case. Is RL case from the ABL insert functions. So we should call RL rebalancing. Okay, else means the other case. The other case. It means it is something like this. Hold on. So it is something like this. The right subtree of this node is longer than the left subtree. Then the right part is longer than others. So we have double R case. So we have to call RR rebalancing. But when we insert into the ABL functions, we had left rotation function. And likewise, in the left rotation function, we took care of LL and LR case. But likewise, we can implement right rotation. And in this function, if this function is symmetric to these functions, okay, then in this function we can take care of both cases. This is it. Now let's talk about the complexity of ABL. So whenever we insert or delete, if it breaks the condition constraint of ABL tree, then we actually rebalanced every time. Okay, then can we get some benefit of this hard work? Yes. Okay, we have 3 different data structures here. So first one is a hash table. We didn't talk about this hash table in this semester, but at the end of this semester we are going to talk about this hash table. Okay, don't worry. And let's just compare binary search tree and ABL tree. So as you know, usually on average binary search tree has log n time complexity, but we had worst case. In that case, binary search tree is just linked list, and we have to check all the nodes. Okay, so the worst case we need the n time complexity. And in the ABL tree, for the worst case, just log n is enough. When we search one key, then this ABL tree is kind of well balanced. So the height of this ABL tree is basically log n. Okay. And then let's think about the overhead. When we insert or delete, then whenever we insert or delete, there is overhead, right? So if it breaks the constraint, then we have to rotate. But this rotation operation takes just constant time. Okay, we just change the pointers. Okay, so it takes just constant time. So in a big annotations, when we talk about the time complexity, we just ignore that. So ABL tree is better than the binary search tree in general.